chapter 5 and chapter 6. What did we learn? Okay, I'm looking at the chat window. Yes, we learned probability. Yeah, thank you, Jason. Christopher, okay, very nice. Hector also remembered probability. Christopher remembered z-score. The z-score is critically important, right? When last week I already told you that's a concept we're going to use almost every week, including this week. Yes, Melissa, probability distribution. Yeah, we have the probability and we calculate z-score for probability distribution. That's exactly right. So who can elaborate? Let's see. Yes, discrete and random variable. That's correct. Very good. So who can elaborate a little more? What is z-score and how do we calculate that? Because that's also what we're going to deal with today. So what's z-score? What is it? Anyone? No, don't worry about the symbols. I mean, you can just unmute yourself or type.
Is it the variable minus the mean divided by the standard deviation?
Yes, very nice. Yep, you got it. Yes.
You better get it on the homework.
Yes. It's interesting. The circles in minus. Oh yeah. So it's x minus mu, right? So your x value minus population mean divided by that circles in sigma. That's population, yeah, over population standard deviation. So z equals x minus mu divided by sigma. So that's x value minus the mean over standard deviation. And remember, mu and sigma both are for population, right? So z-score simply tells us in the probability distribution of the population, the x value, that single value, how far is it away from the mean? Is it above the mean? Is it below the mean, right? In unit of standard deviations. That's what z-score is measuring. It tells us where the one single number is given the entire distribution. And related, we also learned how to figure out the probability using z-score. So who remembers how do we figure out the probability if we have a z-score? One minus p-value from, yeah, you can use that. Yes, so if you subtract the tail, you get the left-hand area. Or you simply go to the table, right? We have the standard normal distribution table. So in that table, we have the rows indicating the first decimal place and the columns indicating the second decimal place of z-score. So once you locate the row and the column, then the value at the intersection simply displays the probability of any value lower than or equal to your x value. So that's the probability we learned from last week. This week, like I said, we're going to learn the very, very similar concept or almost the same concept. However, we do not do the calculation in the population today. we apply the same concept of probability distribution, z-score, and the corresponding probability in the context of sample. That's all we do. We're simply migrating everything we learned in chapter 6 now to the context of sample. And this is chapter 7. So from a theoretical perspective, it's very simple. It's a repetition of what we learned last week. Practically, there's a small change in the formula that we just need to get familiar with. But other than that, chapter 7 is a very simple, straightforward chapter. And I would not expect you to struggle too much in this chapter. So let's get started. Just trying to get the windows right. So, okay. Chapter 7 is about the sampling and the sampling distribution. So again, instead of the probability distribution for the population, now we do probability distribution for the sample. So we can start with a few quick concepts, right? As a review, we learned that a population is a collection of all the elements, right? It may be all the students in business school, right? That's thousands of students. While a sample is a subset of a population. So this class, right, is a subset of that population. Or you can say, I'm interested in customer satisfaction. So all your customers, right, thousands or millions of customers is your population. But when you send out the survey, you send out to 500 customers. So you have a sample of 500, right? That's more manageable. So we always have to do the transition between population and the sample. If we don't have population data, we use the sample data to do what we call estimates, just because we don't see 100% of the data, right? Because sample is a portion of it. So we can only estimate. And estimation simply means educated guess, right? We take our best guess. But in statistics, we say we make an estimate. So again, this is the translation between statistics and your plain English. People say, I'll take a guess, right? My best guess is the average exam 1 score will be 82. Well, that's my best guess, but that's my estimate. If I have historic data and I use that to predict the population, I look at the small sample. So when we do the estimate, we usually start with point estimate. So in point estimation, we use data from the sample to compute a value of a sample statistic that serves as an estimate of the population parameter. So we really are only just looking at one number. So the one number may be the mean, right? So if I don't have time to look at thousands of business school students, I only have time to look at 18 students from this class, then, okay, look at the homework average score, right? To use the mean from the sample to estimate the mean of the population. So that's the one value we use. That's the point estimate. And similarly, if we look at the spread, right, the standard deviation, we can calculate that one value, that one number, standard deviation, in the sample, which is S, and make it the point estimator of the population standard deviation sigma. And even for binary variables, right? So again, this is the time we have success versus failure. right? Male, female, living on campus versus off campus, right? Having siblings with or versus no siblings, right? When we have binary variable, we can also calculate the sample proportion and make it a point estimator of the population proportion. So those are the point estimator we can simply produce and use those to make statistical inference. Let's start with one example. So in this example, we're also in the university context. St. Andrews College received 900 applications from prospective students. The application form contains a variety of information, including SAT score and whether the students prefer on-campus housing. So SAT score clearly is this simple random variable, right? That can take any value. Maybe someone gets 1600, someone gets 1650, someone gets 1705 or 1785, right? Could be any number. That's SAT score. But whether they prefer to live on campus is a binary variable, right? That's a yes/no question. So we are going to learn formula that can help us answer these two questions. One is just for the regular mean, the x value, the other is for the proportion that applies to binary variables. So that's the context. So when there are 900 applicants, the director of the admission would like to announce the average SAT score and the proportion of applicants that want to live on campus. However, the challenge we face is the necessary data, right, for 900 people have not yet been entered in the database. So the director has to make a decision based on her best guess, right? Based on her estimation. So now she selected a sample of 30 and use this sample to calculate some numbers. To start with the very basic, she calculated the mean of SAT score, which is 1684. She also calculated the standard deviation just from that 30 students, which is 85.2. And out of the 30 students, 20 of them preferred on-campus housing. So that's a proportion of 0.67. So those are the values we get from the sample, which ideally we want it to be a perfect reflection of the population. But to be realistic, we know that it will be a little bit off, right? Because you're only looking at the 30 numbers, you are missing 870 numbers. So there may be extremely large value, maybe extremely small value, right? The 870 numbers may look different from these 70 numbers. So with this in mind, once the data of 900 applicants are entered in the system, we did the calculation again. So now this time is for population, right? Look at the notation. Those are now all for population. But previously, the notation X bar, S, and the P bar, those are all for samples. So now when we look at population, we get a set of different numbers. And when we put them side by side, we see that on the left-hand side, we have population mean of 1697, which is like 13 points higher than the sample mean of 1684. Not a huge difference, but clearly some deviations, right? Some difference we observe. Similarly, for standard deviation, population standard deviation is 87.4, while the sample standard deviation is 85.2. And then finally, for the binary variable, the proportion for population is 0.72, and the proportion for sample is 0.67. So overall, we see sample statistic or those point estimates, right? Those values are pretty close to the population parameter. But at the same time, we also realize that they are not 100% the same. There's a small deviation, right, from the mean, the standard deviation, and the proportion. Then that's just the nature of this exercise. We're not looking at every single number. We're just looking at the 30. So with this typical process of having a population, choosing a sample from the population, right? Doing calculation in the sample and then bringing it back to the population, making the estimation. With this process of making statistical inference, now we actually get into our new concept of sampling distribution. So expand a little bit of what we just did. We have a total of 900 students, right? We just rank them by like alphabetical order of their last name, right? So, and give each of them a number, right? 1, 2, 3, 4, 5, all the way to 900. So when we did this exercise, when we picked 30 out of 900, it may be just the first 30 students, like, hey, number 1 through 30, right? Their information is entered in the system the earliest. So I just calculate those 30 numbers. So that gets me here. So then think a little bit. What if we were to take a great many samples of the same size? So I don't necessarily have to take a student number 1 through 30, right? I can take a sample of students. Sorry, let me look at the chat window. Chat window. Oh, this was just for your information that we calculated sample mean. I did not. We don't have time to display the whole set of numbers, but yeah, that's how we calculate sample mean. Sorry, let me go back. Yeah, so look at here. So think one more step beyond. If we were to take many samples of the same size, I don't necessarily have to take student number 1 through 30, right? I can take a sample of students numbered from 100 to 130. Or I can take another sample of students numbered from 800 to 830, or I can take a sample of students numbered from 870 to 900. I can take another sample of students numbered 450 to 480, right? So you see what I mean? We can take many samples of size 30. And we know each student perform differently, right? So all those different samples are going to give me a different sample. So we will end up with many sample means. So in this case, right, consider sample mean itself as a new random variable. So now our random variable isn't the SAT score. now just switching into a new situation. Now we have a new random variable, which is the mean of a sample of 30 students. And let's say I'm taking 10 different samples, right? Then I will have 10 sample means, and they are very likely to be different. So if we have a set of sample means, right, make it a new random variable, we can also calculate the mean and the standard deviation for sample mean, right, for this new random variable. And then we can create the probability distribution of the sample mean. That probability distribution is called the sampling distribution. So that's a new term. In order for us not to confuse ourselves, right? A probability distribution for the population, right? For the 900 SAT score. That's what we learned how to deal with last week. This week, don't deal with the raw number, don't deal with the raw SAT score. Now we take different samples and we calculate the sample mean. So in the new probability distribution, the variable itself is the sample mean. And we calculate the center, the spread, right? That's the sampling distribution. So sampling distribution is the probability distribution of the sample mean. When we have this new probability distribution of sample mean, again, which is called the sampling distribution, we can use actually simple method to figure out its own mean and its own standard deviation. Because we learned last week, for every single probability distribution, we need to know where the center is and how large the spread, right, the deviation is. So for this new random variable sample mean, we also need to figure out where is the center, where is how large is the spread. So the textbook tells us the center, the mean of the distribution of sample mean is actually the mean of population. So again, just remember this, the mean of sample mean equals the mean of population. So in your sampling distribution, your center should be the same as your original probability distribution. So that's the easy one. You don't even need to calculate. You just know, okay, it equals the population. The slightly tricky one is the spread, right? How much differences do you have in your data set? So that's measured by standard deviation. The standard deviation of the sample mean distribution or sampling distribution has its own name. It's called the standard error. So again, not to confuse ourselves, in sampling distribution, we have standard error, and that simply is the standard deviation of the sample means. Its calculation is population standard deviation divided by square root sample size. So in other words, sample size will affect the standard deviation in sampling distribution. And we will see that through two exercises. So let's get this started. So, well, first of all, this is only for proof of concept. This is by no means like exactly how it works in real world. I mean, for proof of concept, we make it quick and simple, manageable, so you can actually calculate in class. So that's a caveat. The key is for you to understand the logic behind, but not like question how many, like that's not the point. I make it small and make it manageable so we can actually do it together. So imagine we should be looking at a sample of 30 numbers, right, for a population of 900 students, but that's simply too much. We can't do it in class. So for proof of concept, I give you a slightly different exercise. Now we have a much smaller database. Here we have a population of 10 students in advanced statistics class. So it's a pretty small class, only have 10 students. For the 10 students, their midterm exam score is listed here. So we got the 10 numbers. Assuming you don't have time to handle population, right? Like 900 students, you don't have time to handle that. So assuming you don't have time to handle population, you only have time to handle a sample. What's going to happen, right? So in theory, we want the sample to be representing the population precisely, accurately, right? So we look at the sample and we can estimate and we can make inference for the population. That's in theory. So in reality, does it really work? Can we really trust a sample? If we select one sample, can we just use that number and say the population will be like that? Right, so let's do the experiment. Here, you know the population. That's the 10 numbers. And then, like I said, if we take a sample, we can take different samples, right? So here, I give you 12 different samples. And then I can certainly give you more, but again, to make it manageable, I give you 12 samples. So like sample A, it's 75, 80, 85. Sample B is different. It's 75, 80, and 80. Sample C is also different. It's 60, 75, and 92, right? So on and so forth. Here we got 12 different samples. Now I really want you to practice on your own, and then we compare numbers together. So answer a few questions for me. Number one, what is the mean of the population? Right? Ideally, we want to have enough time to handle population. So what's the number? What's the right number for the population? So we want to calculate that. And then number two, this is going to be a little bit time consuming. What is the mean for each sample? Right? Is sample one a very good representation of population? Is sample two a good representation? Is sample three is, right? So you get to calculate the mean for every sample. And after you do that, the last question is, what is the mean of the sample mean? Because we have 12 samples and you should have 12 numbers, right? Each sample has a mean. So what's the mean of the sample mean is the last question. I give you a few minutes. I will need to get some water for myself. And then we will compare numbers together. I will show you the pattern and explain to you the theory that we just went over together. So a few minutes, then we do it together. Okay, so has anyone figured out what's the population mean?
The mean of the population is 72.
And 72.5.
No, you might have missed one number. What other number? 10? How did you get 10?
Is it 80?
Yes. Yeah, 80 is correct. We're talking about population mean, right? So you add these 10 numbers together divided by 10. So that should get us to 80. Let me share this. So yeah, that's the population, and I simply did the mean calculation. So population means 80, right? That's the right how well the students actually perform. That's like lower boundary of a B minus. Yeah, okay. Right. So that's what it is. So again, think about the logic. If we don't have population data, if we only look at a sample should be a good reflection of the actual situation of the students. So, but is it, right? I was asking, okay, we got 12 samples. Can we trust all 12 samples, or can we only trust some of those? When we look at sample 1, the mean of sample 1 happens to be 80. So it matches population mean perfectly, right? Perfect. If we have sample 1, we may say, okay, yeah, my estimation is the students' performance are at the lower limit of the B minus, but yeah, they're okay, right? So, okay, if you conclude using sample 1, you are good, right? That's a perfect estimation. If you use sample 2 to estimate or to conclude, right, your sample 2 has a mean of 78.33. So it's pretty close to your population mean, close to 80, but it deviates a little bit. If you conclude, you say, yeah, I think the students are probably performing at C plus, maybe, right? No, okay, that's slightly off, but okay. If you look at sample 3, well, sample 3 has a mean of 75 or 75.67. So that deviates even more from 80, right? You have like over 4 points of difference, almost 5 points difference. And that's a letter grade difference. So now you're saying, well, I think they're performing at the C level. But that deviates even more. So if you happen to pick a sample of sample 3, then your conclusion, right here, the estimation is off by a larger magnitude. Well, if you go to sample 4, you get 81.67. So not precisely 80, but pretty close, right? It's also in the B minus range. And yeah, you conclude the same. So on and so forth. You see we got the different values for the sample mean. Right, we got 12 samples and like 12 sample mean value. If you got lucky, right, you got sample 1 or sample 10, you do a very precise estimation. But there are also situations you don't get so lucky, right? If your sample is like sample 3, you are going to conclude, oh, students are performing at the C level. Or if you get a sample 9, the mean is 85, that's a solid B. And you are going to conclude the students perform at the B level, which both are off, right, compared to the actual like lower bound of B minus. So the point I want to make is, if you only have one sample, there is a chance that your estimation is off. Even though there are chances that you do pretty good estimation, right? The 80s or the 79s or the 8, right? So there's a good chance that you do it well, but there are also like a decent situation that you miss it. So does this make sense? Like a single sample may not be as reliable. Yes. Okay. Good. Okay. So that's the one thing I wanted you to understand. Well, so how do we overcome this limit, right? I have a sample, but I can't trust it. That's not very helpful. So how can we overcome this limitation? Now remember the last question I asked you, what's the mean of sample mean? So here, right, remember what we were saying earlier, treat your sample mean as a new random variable. So for this new random variable, right, think about this whole bell-shaped curve, only for these 12 numbers. For this new variable, now we calculate the mean, right, which is the center. Now we get the mean is 80.33, which if we round it down to whole number, right, it's the same as 80. Again, like I said, for proof of concept, the numbers don't match 100%, but at least if I do the rounding, it gets me to the right number. So if we calculate the mean of sample mean, right, also considering sample with larger mean, with smaller mean, right, if we consider that and calculate the average, the sample mean, right, the mean of sample mean equals population. So that's how can we do the estimation. We can use the mean of sample mean to estimate population mean. Or in other words, we can, vice versa, we can also use the population mean to estimate the mean of sample mean when we do calculation. Because in the calculation, I probably need to draw it. Because in the calculation, when you have the curve, right, if this is your sampling distribution, right, the distribution of these 12 numbers, the center, this number, is simply the population mean. Right? Because I mean they should equal, they should all be here. So later when you do calculation, right, how far above or below to the mean in unit of standard error. So to the mean, that value you can simply use population mean, because the mean of sample mean equals to that. So that's the one thing that that's the one example that explained what we're showing here, right? The center, the mean of the sampling distribution, right, is the mean of the sample mean, which equals the mean of the population. So we just proved the bullet point number 2. And now we wanted to prove bullet point number 3. Right? How does sample size affect the standard deviation? Right? Now it's called the standard error. So how does the sample size matter to that? Now we look at a slightly different exercise. It's the same population, same 10 numbers for the population. But now we take a different set of 12 samples. Since we wanted to test how sample mean affects standard error, now we take a sample of different size. Sample 1 and sample 2 are with 6 observations, right? They are really large sample. Sample 3 and 4 have 4 observations. They are smaller, like medium sized, but still pretty good. Sample 5 and 6, even smaller with only 3 observations, but fine. Sample 7 and 8 have only 2 observations. Then sample 9 through 12 And again, just for simplicity, they are really small. They only have one number. So let's do the same exercise. Calculate the mean for each sample here. And see how far your sample mean, right? How far each one of these numbers deviates from your population. Because, or from the mean of your sample mean, which is 80. See how far they deviate. I give you a few minutes. Do it on your own, and then we will look at the pattern together, because there is a pattern. But I want you to do the calculation first. So maybe 2 minutes, calculate the mean for each sample. So let's look at the pattern together. Here. So we got 12 samples, right? If sample, again, sample 1 and sample 2 are really large. So if we calculate the mean for sample 1, it equals 80.5. So it's only 0.5, right, deviating from the actual population. Sample 2, the mean is 79.5, which is also only 0.5 deviating from the true center. And that's really a tiny deviation. And then remember, in order to make it more reliable, we calculate the mean of the sample. Even though we only got 2 numbers, when we calculate the mean of sample mean, right, we got to, again, the right number. The mean of sample mean equals population. So that proves bullet point number 2 again. And then here, if we get to calculate standard deviation, we can already see it's a very small standard deviation, not even 1, it's only 0.7. So very small standard deviation for sample 1 and 2, that's really large. What about the medium-sized samples? So if we look at the samples 3, 4, 5, 6, like look at all them. First of all, look at the sample mean. The sample means are 77, 78, 82, right? So they are somewhere like 2 to 3 points deviating from the mean, sometimes on the left-hand side, sometimes deviating on the right-hand side. So there are small deviations. But again, if we calculate the mean of the sample mean and we do rounding, it rounds to, again, the population mean or the mean of the sample mean. So there's no problem on that. What I do want you to pay attention is now when we calculate standard deviation, we can even just visually see that those numbers are further away from 80, right? There are 2 to 3 points deviation. So the standard deviation is 2.76, which clearly is greater than the standard deviation from sample 1 to 2. So this happens when you shrink your sample size, right, to smaller. But what if we continue to shrink the sample size to make it really small, right? Only look at the 2 numbers, only look at 1 number. If we continue to do that, look at the sample mean here. Sometimes it goes to 86 or 74, 75. If you get unlucky, your sample peaks the extreme value, right? Like 60 or 92 or 88. So now we see the sample mean for small sample is all over the place, right? Some are very far from the actual, like the 92 or the 60. They are very far from the true population mean. So those are not reliable at all, right? If you happen to have a sample 10 and people ask, hey, how do students perform in advanced statistics class? And your sample 10 will infer that, well, students barely survive. They barely pass the class, which isn't true at all, right? The students are getting B minus. So that's just very bad estimation. Or if you happen to pick sample 11, that's also a bad estimation, right? People ask how well they do, and you say, oh, they are like A minus. This class is designed too easy. The average is A minus. It should be designed harder. Right? That's also a bad inference, right? You are not reflecting what the true population mean is. So here, all the small samples, or most of the small samples, are likely to deviate more away from the population. So even if the mean of sample mean gets them closer, but it's still very hard for us to do the actual estimation because the standard deviation is too large, right? You get numbers all over the place, as small as 60 and as large as 92. And with all those variations, you can hardly guess where in this long continuum the actual center is. So the point is, even though the mean of sample mean is still around the population mean, that doesn't change. The standard deviation can vary a lot, and it's purely affected by sample size. Right? The standard deviation of larger samples are very small, but the standard deviation of small samples are very large. So that translates back to the last bullet point, right? The spread. The standard deviation of the sampling distribution, right, of your new random variable sample mean is calculated as population standard deviation over square root sample size. That's how sample size is affecting the standard error. So always remember, now this is called the standard error. If you have it in the context of a sample, it's called standard error. If you only have it in the context of population, then it's just standard deviation. So there is this difference. But I want you to check if you all understand how sample mean is affecting the standard deviation in sampling distribution. So does it make sense when we did the practice together? Yes. Yes, no, everyone? Okay, Brenda's good. Sharina's good. Others? Or do you have any questions? If you have questions, I can, oh, okay. Oh, okay. Well, I mean, if you want, okay. Okay. Or if anyone has any specific question, you can ask here. I'm happy to explain. Yes, no?
So the square root of n would be all of the variables that we're observing?
Remember, small n is sample size. How many observations do you have in the sample?
Okay.
But this is assuming that it's an infinite population based on that formula, correct?
Correct. Other questions? So, I mean, the key is to understand that we are not looking at like the raw numbers. We are looking at the sample mean. So keep in mind the sample mean itself is the numbers we have in the bell-shaped curve. Each number is a sample mean. The numbers are not like test score. It's the mean of these 10 or these 3 students test score. So that's the key. So that's how we get into the concept of sampling distribution. So now we know that in this standard normal distribution of sample mean, that we can then apply the same concept of z-score. So again, remember what's the concept of z-score? How far above or below, right, your value is compared to the mean in unit of standard deviation. So I will write what we learned last week, and then you see how we change it to this week. So last week, when everything is for the population, right, how far your individual x value is, how far above or below from the mean in unit of standard deviation. That's last week for population. But this week for sample, like I just said, each number isn't a test score. Each number is the mean of 3 students' test score. So it's not just x. Each number now is x bar. So you are saying how far above or below the sample mean is compared to the population, right? Or say compared to the mean of the sample mean, which equals population. So that's in the numerator. Then in unit of standard deviation now changes to standard error because again, we're doing a sampling distribution and the sample size start to affect how far we deviate. So we change our denominator to sigma divided by square root n. So that's the whole calculation of z-score in sampling distribution. So you need to be able to tell when to use which formula. This is also a z-score formula, but this formula we only use it when we don't have the population, but only have a sample. So in sampling distribution, we use sample mean and we use standard error. But if you have population, you still use everything we learned in chapter 6. So can everyone see the difference right here, what I added to the old formula? Are we okay here? Yes. So, okay, good. Hector's good. Okay. So this is the new formula we're going to use today for all the calculations. It's the same concept of z-score, just in a different context of samples. So that's all the difference. And now let's go back to and with central limit theorem. So this I want you to read from the textbook. It explains in theory how we can do this, right? Because like I said, if we have many samples and we have this new random variable, then the shape looks like the standard normal distribution. We can find the center and the spread. So with that, we can use z-score and the standard z-table as we learned last week to do the estimation. So now let's go back to what we just saw earlier. When we saw earlier for this university application data, we see that the population standard deviation is 87.4. And we know that we took a sample of 30. So if we get to estimate from that sample of 30, the first thing is the change in denominator. So now denominator is changed from sigma to sigma divided by square root n. So now the denominator becomes 15.96. Right, so that's the spread. Then a very specific question we can ask is, what is the probability that a simple random sample of 30 applicants will provide an estimate of population mean SAT score that is within plus or minus 10 points of the actual population? So in other words, we know what the actual population is, right? I mean, later on, and we wanted our sample to be close enough to the population. So we defined ourselves this close enough to be plus or minus 10 points. So this will always be given. We will tell you like how good is good enough. Right? So now we decided, okay, plus minus 10 points is close enough. So the question is asking, what is the probability that the sample mean would be close enough? Right? Because again, if you pick different samples, right, student number the 50 to 80 or students number the 280 to 310, right? Like maybe you happen to pick a sample of really smart students whose SAT score are really high, right? And that's not a good representation of the population. So the question is, with so many different samples and different sample mean, what is the probability that your sample mean will be close enough? And when we say close enough, we are limiting it between 1687 and 1707, and that's only because the population mean 1697 is in the center. So when we plus 10 points, it gets us to 1707. When we minus 10 points, it gets us to 1687. So we simply want to figure out the area of the darker gray. Right? What's that probability? So based on what we learned last week, who can tell me the process of solving it? How do we get to this in-between portion? Who remembers that? We learned this last week, and you also practiced in homework. So who still remembers how to calculate the area of the darker gray? Anyone? Try it. How to get to the probability of the middle area? I mean, that's just the area of this darker gray, right? We learned it last week. Go back to last week's lecture, go back to last week's homework. You did it.
Well, you would subtract the area to the left and the right from one. But how do you do it again? You find the z-score for both areas. You go to the table,
yes,
and then you subtract accordingly.
Yes.
I was a little, I mean, I've done it before in my last stats class, but I was still a little like
Yeah, so
going back to
no, yeah, I mean you got the process right. So yes, you start with one number. I mean either one. Start with one number, get the z-score, and then from the z table, you are able to get this area, right? Through the z table. So you do one, and then you do the next, get the z-score, then go to the z table, get the area of this green, because z table tells you everything to the left, right? So you can get the blue, and you can also get the green. Then what you do is you simply do subtraction. After you get right the 4 decimal place, the probability of the blue and that 4 decimal place of the green, you use the blue subtract the green. That's the darker green. That is the area in between.
And a quick question, Professor. So now, of course, the z-score is always towards the left whenever you solve for the equation. Based on the questions that are asked, let's say, for instance, they say, okay, well, we want everything that's above 1707. In that case, that's when we subtract it from 1?
Yes,
okay.
Yes, exactly. If we want everything above, right, that means always a large number. So we're asking the red, and it's simply 1 subtract the blue. Yes.
Okay, thank you for clarifying.
Yeah, of course. Other questions? So now we know the process, right? We need to figure out the 2 z's and the 2 probabilities and then do subtraction to get the middle area. So now I will scroll it back to here. Right. So I got you the denominator, right? Your standard error. And now you just need to do z equals x bar minus mu divided by, right, this number. And then after you get z-score, look up in the table. So do the exercise yourself. I will give you a few minutes, maybe 4 or 5 minutes. And then we will do it together. I really want you to practice this on your own, partially as a review of what we learned last week, and also partially as the practice of the new formula we just learned today. Because you get to know what's x bar, what's mu, right here. I calculated the sigma x bar for you, but you need to be able to put everything in the formula. So a few minutes, then we'll do it together.
Well, it's the 0.4714 is the area.
Very nice.
And again, we're basically just trying to find the z-scores for each one for both the left and the right. So we'll take the actual x and then subtract it from the x bar and then divide it by the is that the standard deviation that you came up with, or?
Yeah, so slightly different. So this is not the x. This is x bar, right? Because we're estimating the sample mean. So this is the x bar minus the mu, right? The population mean, or we call it the mean of sample mean, and then divided by. So it is the standard deviation of the sample mean distribution, and we call that the standard error. But you got it right. Your calculation is right. So if you do it for 1707, that's 0.63, right? That's the z-score.
Correct.
Yeah, and then what's the probability of z equals 0.63?
the 0.7357 that you have there.
Yes, yeah. So if we map it to row 0.6, column 0.03, the table, right? The intersection tells us it's 0.7357, and it really is the whole area to the left. So that's from 1707. Then what do we do next?
We would do the same, but for the other other X, so 1687.
Yes.
1697.
Yeah, 1687 minus 1697, right? So that's the other side. Then divided by standard error, then we get z equals negative 0.63. So we actually can easily do this because it's the same magnitude. We know it's a plus 10 and a minus 10. So as long as it's the same magnitude of your x bar, the z should also have the same magnitude. What changed though is the sign, because on the right hand side is always a positive number, but on the left hand side is always a negative number. So you can simply use the same magnitude, right, the 0.67, but just add a negative sign for the left hand side. But then we do need to go back to the z table. And the z table gives us 0.2643. So that's a small area to the left from 1687. And then, right, like we practiced earlier, if we use a larger one to subtract the smaller one, then we get the middle area to be 0.4714. So now let me ask, how do you interpret this number? We did a lot of work, right? We got 2 z-score, 2 probability. We did a lot of work, and we finally got to the right number, 0.4714. So if people ask you, what does it mean? What is this number? Who can precisely answer that?
For my interpretation, that I would take it as is going back to the question for the probability of students scoring between 1687 and 1707 in that interval. It would be that 47%, 47 point, I forget the number, but 40% of those students would be probably scoring in between that interval.
You are 80% correct. So yes, well, yes, so that's 47%, right, to be falling within this interval, right? This 1687 to 1707 interval. So that's correct, the probability and the interval. Where you didn't get it very precise is, it is not a student score. Remember, we're talking about the sampling distribution. So each number here is a sample mean. So we are talking about the probability that a simple random sample of 30 applicants will have the mean in between these values. So it's a sample mean having a probability of 47%, right, something like that, to be within this interval. It's not an individual student score. It's a sample mean. It's calculated from 30 students.
Okay, so the precise method, or the precise answer that I'm leaving out of my answer, I got the interval, I got the probability right, but I need to make sure that I'm more specific about this is not the entire population. This is a sample mean that we're looking at, right?
So your interpretation is that so the probability of 47%, right? It is the probability that a sample mean of 30 students fall within the range. It is not the probability that one student's SAT score to be within this range.
Okay, thank you.
Yeah, sure. So, and I'm trying to make it easier to understand. So look at the exercise we did before, right? So imagine we have so many samples, right? And then here we have a sample size of 3, but imagine we have a sample size of 30. These are the sample means. So we are saying the probability of one of these numbers fall into that range is 0.47. It is not the probability that one of the original number to fall into. It is not what I'm highlighting here. It is the probability that like one of these numbers fall into this small buffer zone, right? We give ourselves a 10 points buffer zone.
Got it.
Yeah.
So we're just testing the efficacy of our sampling, right?
Yeah, we're really just testing sample mean. Yeah, it's not about the individual students. It's about the sample. Because the underlying logic behind this, we want to use sample mean to estimate population mean, right? We wanted to see on average, how does everyone perform? So it really doesn't have too much to do with one student. Like we're looking at on average how they do. So that's why we use a sample mean to estimate. And that's why the final interpretation needs to go back to sample mean, not to the individuals. So does this make sense to everyone? And it is important because that's all like why chapter 7 is different from chapter 6. That's the only difference. Otherwise, you just do everything in chapter 6. the difference of chapter 7 is now it's not about the individual number. Now it's a whole new distribution of sample mean. Yeah, no, I know it's a little tricky, right? We haven't done this before, right? We previously only take one sample and you get there. But today, through this example, we just saw one sample sometimes isn't reliable, right? Your one sample may be off by a lot. And the only reliable way is you take many samples and you create a bell-shaped curve from these many samples, and then you find the center. And now you see, based on that, what's the probability that we get it close enough? So it's just trying to get us there more precise. Okay, I see. Okay, Marcus got it. Julio. What about others? Like, don't be afraid to ask a question. I mean, we're such a small class, and I told you today we have more than enough time. So I'm happy to repeat or explain again if you do have questions. Everyone good? Yes. Okay, good. Well, let's do this. It's 12:27. And then some of you are still digesting this problem. So I'll give you a slightly longer break as you still digest and make sure you yourself fully understand what we are trying to do here. Get some water, stretch your legs. We come back at 12:40, but in between, make yourself feel comfortable. Yeah, water break, stretch break. make yourself feel comfortable, and just continue to think. I mean, the more you practice, the harder you think. Ultimately, you will understand. It's just a matter of time. Don't give yourself a hard time. Like, slowly refresh your mind for 5 minutes, then come back. So I will see you at 12:40. Back now? Okay, good. Brenda's back. Okay, we'll continue. Okay, Hector's here. Nice. So we just learned how to use sampling distribution, right, to do an estimate. And through this exercise, we finally concluded that the probability that the estimate of population mean, right, which is the sample mean, to fall within this range, right, this close enough range, is only 47%. So it's actually not a very high probability. We define that, okay, plus or minus 10 points is close enough. That's our tolerance band. We wanted to see how confident our estimation can be if we just take a sample of 30 students, which is a very small sample, how confident that we can predict or we can estimate for the population mean. And now the result tells us there's only 47% chance that the sample mean will fall within this range. So it is not a very high probability, so we can't be very confident about our estimation. Then if we ask ourselves, how can we improve this estimation, right? We want to be more confident and we want to be more precise. We want to be able to provide an estimate that really reflects the population mean. So if we want to enhance our estimation, the one way to do that is to enlarge sample size. So that's usually the easiest way. If we have a larger sample, and also if we know population size, then we can even use the finite population correction factor in our calculation. So this is a small addition to the formula we just practiced before. We only use this finite population correction factor when we know the exact size of the population and when we have a large sample. It doesn't apply to every single situation. So in this example, it would apply because we know the population is a total of 900 students. So we know large, and then yes, we know small, and right, 30 is a small sample, but we can enlarge it. So that's fine. In my example of Cal Poly Business School students, I can also figure out the large. I go to the registrar's office and see how many students are registered for this semester. So that also has a fixed population size. But in a lot of other situations, you can't use this finite population correction factor because you don't know the large. And for example, if you're a customer service, right, you want to see customer satisfaction level. You send them a survey and then you wanted to calculate the mean, like how satisfied are they? You know your sample size, right? Okay, you send out 500 survey, that's simple, but you really don't know the population size. You don't know if 1 million people bought your product or 1,200,000 people or 1,235,000 people, but you have no idea. So in that case, you don't know population size. So you can't use finite population correction factor, and you basically have to assume an infinite population. And similarly, if you are interested in individual income, right, you wanted to take a sample and estimate income level for Southern California. But the challenge here is you don't know exactly how many people, right? There's mobility, people move around all the time. So you don't have the exact number. And if you don't know exactly how many people live in Southern California, you can't use this. So not every single time you can use a finite population correction factor. But when you really know your sample size and you do have a large sample, to use the finite population correction factor will help us shrink the deviation in our sampling distribution. Because we know if it deviates a lot, right? If the number is all over the place, it's hard for us to estimate. But if we know it doesn't deviate, all the values are very close to each other, right? Then we can safely, confidently make an estimation. So this component, this square root large n minus n over large n minus 1, right? Population size minus sample size over population size minus 1 in square root. When we multiply this in the denominator, multiply that with the original standard error, the standard error will be reduced. In this very specific situation, let's see. So how can we enhance our estimation? Like I said, 30 is too small of a sample. So let's select a larger sample. Select a sample of 100 applicants out of the 900. So now we have more than 10% as our sample. That's a decent sample. With that, and also this finite population correction factor, now the denominator is calculated in this manner and is changed to 8.2. So how much of a difference does it make? Before we increase sample size, right? At the beginning, when sample size was 30, and the standard error was 15.96, you can see this wide and flat distribution. Right? It's very wide, so you see the right tail and the left tail, they deviate very far from the mean. So if your values are all over the place, right? The SAT score, average SAT score, if it is all like between 1500 to 1800, if you have a 300 point range, it's going to be very hard for you to figure out what's the exact value, right? If it's too wide. That's not the ideal situation. But now after we increase the sample size to be 100 and put together the finite population correction factor, the standard error shrank from 15.96 to 8.2. So that's how much, right, your sample mean deviates from the population mean. So now you see the very tall and narrow distribution. That's after we increase sample size. It means now the sample means are all around this middle value. They don't go as far. They don't go all the way to 1800 or 1500. They are pretty close to the 1697. Maybe they go to like 1600 to 1750. That's about it. They don't deviate too much. So when you have a smaller range and you got a lot of values all very close to 1697, it's very, very easy for you to estimate. You see, like all the samples have the same mean, then that's probably right the population. So that's the underlying logic behind. We want to have a small standard error. So the distribution have a very small spread. The values are very concentrated, and the concentrated value helps us determine where the actual center is, right? It helps us estimate. We do not want to have a large standard error because that makes the distribution very wide. It covers too many values, and with too many values, it's hard for us to estimate. So the wide and flat distribution is what we don't want to have. The tall and narrow distribution is what we do want to have, and that one helps us do estimation with more confidence, right? Because now, let me show you exactly how does that increase our confidence. Previously, there's only 47% chance we get it in the range. But now with the distribution, like being very concentrated to the center, with the same buffer zone, right? The same +10, -10 buffer zone, doing the same calculation, but just a different standard error. Now the area in between is increased to almost 78%. So now there is a 78% chance that the sample mean will provide us a close enough estimation to the population mean. So 78% of the chance our estimation is going to be good. Versus previously, when we did the calculation, when it's wide and flat, there's only 47% chance that our estimation is good. So we improved that by like 30%. So that's the value of increase your sample size and also apply the finite population correction factor. So does this make sense? Like the change in standard error and how does that affect the probability in the middle area, like affect our estimation?
Yes.
Yes. Everyone else? Good. Some of you are really quiet today. Melissa's good. Okay, nice. Julio, good.
And just again, to reflect off of that, we had to get that standard error by using that finite population formula, correct?
So when we calculate that, we first calculate the original standard error, right? That's the sigma divided by square root n. So if we have the population size, we multiply population correction factor to that. So it's just one more multiplication in your denominator. Because this whole thing, this standard error will be in the denominator. So just one more multiplication of this.
Okay, awesome, thank you.
Sure. Everyone else good? I'm trying to recognize the names. Oh, Ken, you have been pretty quiet today. You got everything at home? Yes. And Jason got everything? Yes, no? Hector is good. Okay, nice. Christian, nice. Christopher, okay. You guys okay? I mean, I see your names every week, and in some weeks you guys are more proactive with feels like today most of you guys are quiet. Don't know if you get it. Yes, no? Mikhail, yes. Okay, if you don't ask questions, oh, okay, good, good, okay. If you don't ask questions, I am going to move on. I just don't want anyone to be left behind. So, okay, if no questions, then let's get to, where is it? Oh yeah, sorry. So that's about sample mean estimation in sampling distribution. On slide 34, I give you one more exercise for you to do it on your own. So it's exactly the same concept using the same formula. I want you to be able to identify, like, okay, what's X bar, what's mu, what's sigma, what's n, right? And then use the formula to figure out the Z and figure out the probability. That's on slide 34. Once you do that on your own, then check your answer with what I give you in slide 35. I give you exactly step-by-step calculation. Once you make sure, right, you got the right number, or at least you understand what I'm doing, then it's a confirmation that you are ready to do homework. Don't do your homework before you check your knowledge level. So slide 34 and 35 is your own knowledge check. When we do it together in class, it's easy and straightforward and explaining. But when it goes back to you, right, tomorrow when you wake up and forget half of the material, like, can you refresh your memory? And so do this knowledge check first, then do the homework. Because I want you to get good score in the homework. I don't want you to like be still confused and make mistake. So do the knowledge check. Slide 34, 35. That's for you. Then let's move on. So we've done that. We've done this sampling distribution for the mean. Now we wanted to apply the same concept for the binary variable. So for proportion, it's the same process. We have a population. We take the sample from the population. We conduct all the calculation in the sample. And then we take the sample statistic to estimate the population parameter. So from the flow chart, you can see it's the same process. The only difference is in the calculation, right? When we learn about the binomial distribution, when we learn about the binary variable, right? Success versus failure. I told you because it's a very special situation, so we use different formula, right? Compared to the random variable. But other than that, everything else is the same. We use the same logic to calculate the z-score, and we use the same table to figure out the probability. So when we have this binary variable and use the concept of proportion, in this example, right, we see that, okay, among the sample of 30 students, 20 out of them, which is 67%, prefer on-campus housing. So that's from student number 1 through 30. Imagine if we choose a student number 300 to 330. Maybe only 18 out of them prefer on-campus housing, but the other 12 prefer off-campus. If we choose a student number 850 to 880, maybe 22 of them prefer on-campus housing, right? So depending on the sample we choose, we are also likely to get different proportions. We know that later when all 900 data points are entered in the database, right? We know that for the population, 72%, right, prefer on-campus housing. So that's the target we want to hit. If we take a sample, we want the sample proportion to be 0.72 or to be as close as possible. Right? So we want that to happen. We don't want the sample to be too far from 0.72. If the sample says 0.5, that's way off, right? The school isn't doing the necessary preparation to have this many students like leaving in the door. So we want the sample to be as close as possible or at 0.72. But again, there's no guarantee on that. How can we make sure, right? Or how can we estimate if a sample we pick is properly reflecting the population proportion? So same question, how can we know if the sample, like SAT score, is reflecting the population? So we use the same technique, right? Take multiple samples, calculate the sample proportion from each of them. And then we take the average, right? Take the center of the multiple sample proportions, right? Maybe some are 50%, some 55%, 60%, 68%, 70%, 72, 75, 78%, 80%, right? We got all different sample proportions. So we take the mean of the sample proportion, and that mean, right, that center should equal to population proportion. So that's the center of the sampling distribution of proportion. Then we also look at the spread, right? What's the standard error in proportion? Like I said, that's where we have the difference, because standard deviation calculation of a binary variable was different from what we learned before. Weeks ago, we learned that the standard deviation of a binary variable was probability of success multiplied by probability of failure multiplied by sample size. That's the standard deviation for the population. Now, when we get it into the context of sample, and knowing that the sample size is also going to affect this value, it's going to affect how much it deviates from the center. Now the formula changes to square root probability of success multiplied by probability of failure divided by sample size. So sample size is always in the denominator when it comes to standard error, because the larger the sample size, the smaller the standard error. The smaller the sample size, the larger your standard error, the larger your deviation. So it's always an inverse relationship. And it's easier for you to memorize, right? The sample size is always in the denominator because it's always an inverse relationship. So that's the only new component in the calculation. So then when we calculate the z-score, it's the same logic that we measure how far above or below the sample proportion is, right, compared to population proportion. Or again, population proportion is the mean of the sample proportion in unit of standard error. And again, that's a standard deviation divided by square root sample size. So that's a new calculation. So z-score calculation for the binary variable, right, for proportion is sample proportion minus population proportion divided by standard error for the binary variable. Slightly different calculation, but the same structure, same concept. And now let's put it in, and also same finite population correction factor would also apply to proportion. Right? Square root population size minus sample size divided by population size minus 1. So that's all the same. Now let's dive into our calculation. And so here we know that for the population, the proportion is 0.72. And then when we select a sample of 30 and do the calculation and the estimation, we wanted the estimation to be close enough. And when we say close enough, we decided to be within plus or minus 5%. So think about how large that interval is. We start at 0.72. So plus 0.05 gets us to 0.77. Then minus 0.05 gets us to 0.67. So in other words, we're asking ourselves, what is the probability that a simple random sample of 30 applicants will give us a proportion that's between 0.67 and 0.77? How likely our sample proportion is going to be close enough? How likely? Is it like 90% of the time, or is it 50% of the time, or is it 10% of the time, right? So we're still trying to figure out the probability in between this 0.67 and 0.77. So if I get to show you in the chart, right, it will look like this. The middle, the center is 0.72. Then we created our tolerance band to be 0.67 and 0.77. Then it's going to be exactly the same calculation, right? Figure out the z at 0.77, then the probability. Then figure out the z at 0.67, then the probability. And finally, you use the probability of the larger area, subtract the probability of the smaller area, then you get the middle, the darker gray. So that area is the probability of your sample proportion falling within that range. So does this make sense? Like almost a repetition of what we did half an hour ago. Yes? Yes, no? Yes? Okay, nice. Marcus, Jason, Shalina, nice. Hector, good. Okay, good, very good. Brenda is good. Okay, very nice. I don't know whose iPhone, but yes. Okay, so here I will give you maybe 4 to 5 minutes to see if you can do that on your own. I have already calculated the standard error, right? I've already calculated your denominator for you. With that, and with this chart, in 4 or 5 minutes, see if you can get to this value, the probability of the in-between. And after 4 or 5 minutes, we will do it together. So even if you don't get this, not a problem, we are going to do it together. But I do want you to try it on your own. That's the best way you understand it. So look at what's the center, right? What's your X bar? Then what's your denominator? Get the z-score, get the probability, and then do the calculation. So we'll see. If anyone finished, I mean, feel free to post the value in the chat window, right? If any of you get the z-score, post in the chat window, or if you got zero probability, right, of the larger area or the small area, post in the chat window. And then we'll just cross-check there's no punishment even if you get it wrong. But if you get it right, that's great. Everyone see, oh, okay, you got it like so quickly. You'll see who can post it really quick in the chat window. 4 or 5 minutes on your own, and we'll do it together. Anyone getting the Z thing? Okay. Oh, nice. Marcus, you're quick. Wow. Yep. Yep. Good, good. You're pretty close. Yeah, if you are close to that, like second, third decimal place, then it's probably just a rounding issue. Like I would not be concerned. And later we'll work through the steps together, but I think you got it. Yeah, that's close enough. Who else got it? Or how many of you got the Z score for like one of those? What's Z? Anyone? Mm-hmm. Yes. Very nice. That is the Z-score calculation. Yep. Very nice. Okay, we'll just do it together. Don't see others participating. But... okay, so we get to do exactly the same thing, right? Calculate the Z, map it to the Z table. So for the upper limit, like Marcus posted, we use 0.77 minus 0.72 divided by 0.082, right? Sample proportion minus population proportion divided by standard error. So Z equals 0.61. Then when we go back to the Z table, we map it to row 0.6 and the column 0.01. So the intersection gives us 0.7291. And as you could see, that's the entire area to the left for the larger value. And similarly, we calculated for the left-hand side, right? And because it's the same magnitude, so the magnitude of Z would be the same. It must be 0.61, but we have to flip the sign. So it's negative 0.61 for Z. Then in the table, we have to look row negative 0.6 and the column 0.01. So that gets us to the area of 0.2709, right? That's the area to the left of the small value. Then just as we did for the earlier exercise, we use the larger area to subtract the small area. And we get the middle area of 0.4582, like here. So then, again, the key is to interpret this number. Okay, the final number is 0.4582. What does that mean? The probability, right? It's a probability. So the probability that the estimate of population proportion, which really means the sample proportion, to fall within the range of 0.67 to 0.77 is 0.4582. So in other words, we're saying there's a 45% chance that the sample proportion of 30 students, right, the proportion of a sample of 30 students will be close enough to the true population proportion. So again, it's not a very good estimation. It's not even 50%. It's 45% of the chance. But given that you have a very small sample, you only have a sample of 30, it's understandable that your probability isn't that high, right? So 45% of the chance that your sample is going to provide a close enough estimation for the true population proportion. So 55% of the chance your sample proportion is going to be further off. That's always the same, right? If we connect this to what we're going to learn next week, this is really just our confidence level. If only 45% of the chance we are going to be right, then we're only 45% confident. Next week, we're going to talk about how to adjust the confidence level. How can we be 90% confident? How can we be 95 or 99% confident? So that's about next week. Next week, all about the range, right? The interval of estimation. But it builds on top of what we learned today, right? To look at a sample, to decide a point and go from that point. So that's all for the exercise here on estimating proportion. Again, for you to do a knowledge check for yourself before you do homework, on slide 52, I give you another example, and I also post the solution on the same slide. What I want you to do is, later, right, after you take a break or tomorrow when you get refreshed, your mind refreshed, read the question and solve it on your own. See if you can solve the whole question on your own. If you are able to do that, that means you are good, you are ready to do homework. If you can't solve it or you get it wrong, just see how I solve it and then try to understand, like, what did I do step by step and how to get the final answer. Once you fully understand this, right, and then review the lecture notes, review the textbook, you should be in a good shape to do homework. That's the key of this chapter. In the lecture note, I also give you a quick summary of like the theoretical concepts of different sampling methods. But like I mentioned earlier, like I mentioned on day one, right, for the scope of this class, we do not practice data collection. So I will not ask you to actually collect a sample and put together the data. This is for you to know. In the future, when you take advanced classes or do a project, you know how to select a sample and put together your data. But for the scope of this class, you don't need to actually do it. All you need to do is read through, just skim through and make sure you understand what we're talking about. So you will not have this in the fill in the blank, but you may have one or two questions in multiple choice session. That's the only way I can check that you read through, right? But yeah, don't expect any hard question in like the selecting sample, those and other sampling methods, those theoretical foundation. Spend more time on understanding the formula, understanding the logic behind the formula, and how to use that to calculate the sampling distribution of the mean and the proportion. So that's the key for chapter 7. Next week, we're going to talk about chapter 8, right? How to do interval estimate, not just one point, but the whole interval. very closely related with what we just practiced today. It would be very helpful if you quickly go over the textbook before you come to class, so you don't struggle with what I lecture. You can understand it quickly. That's how you can prepare for next week. And like I mentioned earlier, the week after next week, which means October the 9th, we will have our first exam. So next week at the beginning of the class, which means do not be late for next week's class, I will remind you about the format and the scope, all the logistics about the exam. There will not be any surprise. It's covering all the chapters that we discussed together. It's a total of 6 chapters. Chapter 1 really doesn't have too much. So it's more like a collection of 5 chapters. It is made manageable, but you do need to practice time management, which I will discuss more next week. But I just want you to be prepared. And if you want, you can start reviewing things like even from now, right? It never hurt you if you start preparing sooner than later. Lecture note, the textbook, and all the past homework will be the best resource for you. I will not ask anything like you've never practiced before. All the questions will be discussed or at least from the textbook. There may be questions even the same from homework. There is just an assessment of how well you've done in the first 5-6 weeks. So just keep that in mind. Do the exercise and make sure you understand the knowledge. Then you will do it like quicker and then with higher accuracy. That's all we have. Any last minute questions?
Professor, is it okay if I speak with you after the class leaves?
Oh yeah, sure. I'll stay after.
Okay, thank you.
Sure. Anyone else? We're good? Yes? Okay. Yeah, everyone's very quiet today. So I'll give you a few minutes back. Enjoy the weekend. Don't forget homework. Don't forget reading the textbook. And I will see you in a week. Bye, everyone. Thank you. Bye.